Hello, everyone. I want to talk about section 9.1 on gas pressure. The learning objectives for this session define the property of pressure, define and convert among the units of pressure measurements. Those are the two that we'll focus on. We will look at these others a little bit, but they're not something that you will be tested on. So to start with, there are several, I shouldn't say several, there's actually exactly four things that are important to understand about gases. It turns out the one we haven't talked about yet is pressure. So we want to start our conversation on gases by discussing what we mean by pressure. So I think we all have an intuitive understanding pressure being something that is stressful that we don't want in our lives. And that's one kind of pressure. But scientifically, there is a definition we'll be using. We actually already have a lot of pressure in our lives simply by living on the earth. So the pressure of the gases in the atmosphere is always going to be present. And that's because we have, we have an atmosphere full of gas molecules. If we were on a planet without an atmosphere, we wouldn't have that pressure, but we also wouldn't be able to breathe. So it's kind of a trade-off. It turns out that the atmospheric pressure that we live in is equivalent to having a bowling ball on your thumbnail. So that's the pressure we are always living in. Now, it might not seem like it's that bad, and the reason is because we also have the pressure is stabilized, right? So we have pressures on one side, pressures on the other side, and they kind of balance out. But if we were to apply a vacuum, we would see how much that pressure can actually do. So this pressure in the atmosphere is because we have gas molecules, and those gas molecules are flying about and they're colliding with surfaces. And each individual collision doesn't do a whole lot in terms of the pressure, but if you continue to have those collisions, they kind of build up. So there's just a lot of them, and they build up. Mathematically, this is how we would define pressure. Pressure is equal to force divided by area. Now, this is something we're not going to really explore in detail in this class. This is something you'll be getting into more detail on in a physics class. We haven't really even talked about force that much. We do know a bit about area. But this is kind of conceptually what pressure is. So when we say force divided by an area for pressure, you have all of those gas molecules colliding with the surface. So over the area of that surface, that's what the pressure is coming from. There are some examples here in your book about calculating pressure for various situations, but we're not, again, this is a level of detail I don't want to get into. This is something in your physics courses, if you take them, that you'll do these sorts of calculations. For the measurement of pressure, we have several units. So the SI unit is technically the Pascal. We're not going to use it very much in this class, but that is equal to 1 Newton, and Newton is the measure of force in the SI system per meter squared. We often, instead of using pascals, will use something like pounds per square inch. So you might, for example, be aware of this. When you're driving a car, you have to have your tires inflated to a certain PSI. So that's what that's measuring. What is the pressure inside of those tires? And one thing I should mention here, when you're doing that, that's called the gauge pressure. So that's telling you what is the pressure inside the tires that is greater than the pressure outside of the tires. So you're subtracting out that pressure that we're always living in. And then actually the one we'll be using the most is called the atmosphere. This is a measure of kind of the average pressure at sea level, and that is taken to be 1 atmosphere. Now, it's not, we know that that's going to vary from day to day, right? So that there is a definition for where, which, how that relates to other things, not just, okay, if we go down um, to Avia Beach, whatever the pressure is there, that's 1 atmosphere. This table is showing the relationships between the various measures of pressure. And you basically would need to be able to do conversion factors between these. So if you're given pascals or kilopascals, do you convert to atmosphere? If you're given torr, do you convert to atmosphere? You don't have to memorize these conversions. They would be provided for you. You simply need to be able to do the conversion factors in a way similar to we've been doing this entire semester. I will say that the most likely ones for you to see are the atmosphere. This one will be kind of our go-to. And then the torr and inches of mercury. These are essentially the same thing. And I'm sorry, not inches of mercury. I should say millimeters of mercury. So torr and millimeters of mercury are essentially the same thing. So 1 millimeter of mercury is equal to 1 torr, and then that is equal to 760 torr is equal to 1 atmosphere. And when we say millimeters of mercury, you might wonder, well, that's kind of a weird measurement. We'll see here in a minute why we would use that as a measurement. So simply be able to do the conversions similar to any conversion we've had before. So if you're given this information, put things in the correct units based on the question you're looking at. Okay, so why do we talk about millimeters of mercury? The way we can measure the pressure on the Earth is with something. There's a lot of ways we can measure pressure on the Earth, but the kind of the traditional method, the oldest method, is using something called a barometer. And the way a barometer works is you have a glass tube, and there's a picture here of a barometer, so we'll talk about that. You have a glass tube, and it's closed on one end, open on the other end, and then we insert it into a liquid. And before we do that, we actually want to make sure we have a vacuum inside of it. So somehow we create a vacuum that will suck all of the gas molecules out of that glass tube. Once we've done that, we're not physically going to do this ourselves, but once that is done, it is then inserted into a liquid. That liquid is subject to the atmospheric pressure. So the atmospheric pressure is pushing down on whatever that liquid is. Inside of the tube, there is no atmospheric pressure because we created a vacuum. There are no gas molecules there to collide with the surface. So what's going to happen is that atmospheric pressure is going to push the liquid, and it will go up into that glass tube. And the distance that it goes into that glass tube is something we can measure as a measure of pressure. So we measure how high did it go. So we're showing two examples here of barometers, one using mercury. So with mercury, because it is so dense, we can measure that distance as 760 millimeters. So we're measuring a distance, but that distance is actually a measure of pressure. So if you look at that up here, that's what we're talking about. We could do inches or we could do millimeters, often done in millimeters. So when we say a length as a measure of pressure, we're measuring how high that liquid goes within a barometer. Now, of course, with mercury, there are issues. It is very toxic. We try not to use it if possible. We do have some barometers in the classroom, but there is good reason to think, well, maybe we don't want to have a barometer somewhere. And so you might think, well, why would we use mercury? Why don't we use something like water? Wouldn't water do the same thing? And the answer is yes, water would do the same thing. If you have a container of water and you have a vacuum in a tube and you invert the tube into the container of water, you would expect atmospheric pressure to press that water and cause it to rise inside of that tube. Um, Water would actually be even a better way to measure pressure than mercury would. The challenge, though, is that instead of something that goes about 2.5 feet, this would go about 30 to 35 feet. Um, that's how high it would be. So we would basically need a 3-story building to contain a barometer using water as the liquid. Now, it would be great if we had that option. We don't have that option here. But it would actually be a better barometer because when we make that measurement, right, you're going to have more significant figures than you would with a mercury barometer. So ideally this would happen, but with the constraints of architecture, it doesn't happen all that often. There are places where they do have water barometers in some universities. So the equation, and we're not going to focus on this too much, for why it would be different with mercury and with water. The pressure is equal to the height in the tube times the density of the liquid in the tube, and then times the gravitational constant. Again, some of these equations you'll be using in more detail in a physics course. There's an example here of calculating barometric pressure based on the height, so you can look at that example. I'm going to skip over the manometer part. It's somewhat similar, but used in an experiment because I did want to also talk about meteorology. And so we know when we look at the weather, it will talk about the pressure is rising or the pressure is dropping in atmospheric pressure. I did want to make a note of this, and it actually doesn't affect us too much in the Central Valley because we are fairly close to sea level. But these are often, when you hear it on the news, it is when they report the weather, they are recalibrating it in a different way. So it's based on elevation. So they correct it. So we know that, for example, on the top of a mountain, the atmospheric pressure will be lower than at sea level because you have fewer gas molecules kind of piled up on top of your head when you're on a mountain than you do at sea level. That's kind of a rough way of understanding it. That's not exactly what's going on. But essentially what happens is when they report the pressure, it's not the actual pressure. They are making adjustments so that they can report pressures anywhere in the country, and it kind of means the same thing. So if you're at the beach or if you're in the Rocky Mountains and there's a report of a weather pressure, you're kind of going to interpret it the same way. So that's a little bit about something that goes into effect there. There's some details here on the different components of the atmosphere. We're not going to cover that in this class. That's more of a physical science topic. So I wanted to talk a little bit about that in case that's something, if you're traveling somewhere in the mountains and you're thinking, oh, well, what about this difference in elevation? That's already been accounted for. So that kind of wraps up this first section on gas pressures. In the next section, we'll be taking that and incorporating it with the other things we can measure about a gas to understand them in a little bit more detail.